STA 3532 Introduction to Statistical Quality Control, Chapter 4 Control Charts for Attributes. In the previous chapter we discussed about control charts for the variables. In this chapter we considered about attributes. You know that each and every quality characteristics cannot be represented in numerically. Therefore we have to classify then those quality characteristics into according to some specification. Then here we considering about conforming and non-conforming, and the terminology defective or non-defective is often used to identify those classifications of product. So the defectives and non-defectives we consider we divide it into two groups, and the terminology conforming and non-conforming has become popular. Quality characteristics in this are called attributes. So attributes we called conforming and non-conforming. So we are one by one we can understand through examples. And this basically in this lesson we are we are considering four types of charts: P chart, NP chart, C chart and U chart. So the then this is the way of identifying those charts. These are the control charts for the attributes. So then if the given question that is based on the word non-conforming, that is non-conforming, you have to use the P chart. Right, when we are doing the exercises you can understand now. Just remember that if that is somewhere in the question that is non-conforming, then it means that are P charts. If in the question it is mentioned as number non-conforming, it means you have to use the NP chart. And non-conformities is there, you have to use the C chart, as well as the number non-conformities per inspection unit it is mentioned in the question, so you have to use the U chart. The chart for fraction non-conforming, that is the first type, that is we are going to talk about the P charts, that is the charts for the fraction non-conforming. The fraction non-conforming is defined as the ratio of number of non-conforming items in a population to the total number of items in the population. So we have to take the fraction as, so here given as ratio number non-conforming in the items in the population to the total number of population. It means if you have number non-conforming 10 and total number of in the population is we'll take 10 is the non-conforming items. If total number is 100, so we can take fraction as 0.1, right? So that is the way. Usually express the fraction non-conforming as a decimal, as I mentioned above. So normally we are representing as a decimal, although occasionally percent, if we need, we can convert into the percentage. 100%, then we can take the percentage also. The statistical principles underlying the control chart for the fraction non-conforming are based on the binomial distribution. So then basically this control charts are based on the binomial distribution. So this is the you know that what is binomial distribution. Anyhow, I am going to revise again what is binomial distribution. A quality characteristic follows a binomial distribution if these are the conditions: all trails are independent, all trails should be independent, and also either each outcome is either success or failure. So in the binomial distribution, you know that if it is a success or failure, we are using the binomial distribution. So each outcome is either success or failure. The probability of success of any trail is given as P, then probability of the failure is 1 minus P, right? And probability of the success is constant. That probability of the success is always constant. That is the equation we are using in the binomial distribution with the parameter n not equal 0 and p between 0 and 1 given by p of x equals n, this equation, and the mean and the variances of this distribution, mean is mu equals to the np, and variance is equal to np times 1 minus p. If we developed the fraction non-conforming control chart, it means p chart, this can be used, that binomial distribution can be used in here also. Then n equals number of units product selected at random, and d is equals number of non-conforming units for the sample, and p is the probability of the selecting non-conforming unit for the sample. Then we can derive this from the binomial distribution. Then pd equals x, then all the other things are same. So this is then we can develop the fraction non-conforming control charts. Then the sample fraction of non-conforming is defined as the ratio as the ratio of the number of non-conforming units in the sample d to the sample size n, that's p hat equals d over n, right? So this is the equation. So this is the sample fraction of non-conforming finding. So if you are doing the examples, I can explain this, what is it, and this is the way of finding. And p hat is the random variables mean and variance. Mu equals p, right? That's the probability we are taking as the mean, and variance we can find sigma square equals p times 1 minus p over n. These are the equations we have to use when we are solving the problems. So remember those equations and understand what are the instances we have to use those equations. In chapter 3 we discussed the general statistical principles on the Shewhart control chart is based. In chapter 3, the previous chapter, we discussed about these control charts, X bar charts, R charts, and all those charts we discussed. If the W is a statistic that measure quality characteristics, and if the mean of W is mu W and the variance of W is sigma W square, then the general model of the Shewhart control chart as follows. This is the Shewhart control charts we discussed in the previous chapter. This is the general form, where UCL is equals mu W plus L sigma W. That center line is equals mu W, and lower control limit is equals to mu W subtraction L times sigma L sigma W, where the distance of the control limits of center line is multiples of the standard deviation. So then this is the multiples of L is the multiples of standard deviation. So normally we are choosing L equals 3. This is belongs to chapter 3, that in as same as we can use for that p charts if the standard is given, right? If that standard is given, the suppose that the fraction that non-conforming p is known, right? If p is known, suppose that fraction non-conforming p is in the production process, if is known or the specified standard value, then from equation the center line and the control limits of the fraction non-conforming control chart would be as follows. So this then fraction non-conforming chart standard is given if p is known, so we can use these equations to find the upper control limit, center line, and lower control limit. Upper control limit equals p plus 3 times square root p into 1 minus p over n, and center line equal to p. Then lower control limit equals p subtraction 3 times square root p into 1 minus p over n. And if the p is not given, it means standard is not given. So when the fraction of p is not known, then must be estimate from the observed data. The usual procedure is select m preliminary samples each size of n. As a general rule, m should be at least 20 or 25. So the general rule is m equals 20 or 25, but when we solve in the problems, we are selecting m less than 20 or so. If there is di non-conforming units, d means non-conforming units in sample I, we can compute the fraction non-conforming I sample as that is derived from the previous this equation, p hat equals d over n. So we can take p hat I equals di over n, where I equals 1 2 3 to m, and the average of these individual sample staple fractions non-conforming, that p bar we can find equation, any of these two equations are given. P hat equals I equals m I equals 1 to m di over m n o m and o sigma I equals m I equals 1 to m p hat I over m. So then in these two equations, any equation you can use to calculate the p bar. Then if standard is not given, so instead of p you have to use p bar here. That is only difference. If standard is not given, that means p is not known, you have to calculate the p, then after finding the p bar you can calculate the upper control limit, center line and lower control limit, right? Then if we find these control limits, we are calling that as the trial control units. Control limits that are based on the preliminary set of data can be referred as a trial control limits. The quality characteristics is plotted against the trial limits. If any point plot out of the control, again assignable causes should be investigated and points removed. It means after then now we calculate according to these equations trial control limits, upper control limits, center line and lower control limits. We calculate those are the trial control limit. Those are the trial control limits. After that we have to draw the control chart, right? We need to draw the control chart after finding those, right? Now we can draw the control chart, right? We are going to draw the control chart. This is center line, and like this way we using, this is upper control limit, this is lower control limit, and the control chart we can draw this like this way. This is A, this is B. These are normally we are taking trial control limits. Then here given, if quality characteristics plotters again the trial limits, if any point plot out of the control, then you can see here this point is out of the control and this point is also out of the control. Then the assignable causes should be investigated and points removed. So if these are go beyond these lines, so you have to remove. Then here point A and B need to be removed from this control chart, and you have to find the revised limits, right? If some points are removed, then you have to recalculate the control limits. Yeah, with the removal of the point, the limits then recalculate. So we call these are the revised limits. So in these types of questions you have to calculate two types of control limits. First of all, you have to calculate the trial control limits, then we have to check the values. It is better to draw the control chart. Without drawing the control chart also we can find by observing the values. You can find that if it is go beyond the control limits, if it is out of control, so you have to remove those points as mentioned in here, and you have to revise the limits again. This is the example, so we can find those things as I explained in there. The data in the table give the number of non-conforming, here number of non-conforming bearing and seal assemblies in sample 100. Then sample 100, it means here n equals 100 because here given sample is 100. construct a fraction non-conforming control chart for this data. Fraction non-conforming, here given fraction non-conforming control chart, it means you have to develop P chart, clearly mentioned. If any point plot out of the control, if any point, here it's given, if any point point out of the control, assume that assignable causes can be found, then determine the revised control limits, as I mentioned in the previous slide. So here, if assignable causes are there, if anyone goes out of control, so what you have to do, you have to revise the control limits. Here also you have to do the same thing, right? So then we go to the solution. Then here given sample number, number of non-conforming assemblies, number of non-conforming assemblies is given there. So then here now right, here you have to find that here some fraction non-conforming, we can find using this equation, that what is it, p hat equals di over n. So I can use the equation p hat I equals di over n. Then here these are the here p hat I, here also p hat I, we can find di over n. Then I can p1 equals d1 over n. d1 equals 7, here d1 equals 7, n we here given n equals 100, n equals 100, here we wrote n equals 100. Then we can find 0.07, this is the value, and p2, that is d2 over n. Then d2 over n, d2 means 4 over 100, that is 0.04. likewise you can find all the values. Here 7 divided by 100 0.07, 4 divided by 100 0.04, 10 divided by 100 0.1, then 7 divided by 100 0.07, as well as the 20th one 12 divided by 100 0.12. after that you have to find, you have to calculate the total of these two. If you added the number of non-conforming assemblies, the total is come as 117, and it means this is what you called sigma I equals 1 to here 20, no, 1 to m, no, okay, 1 to 20 di, that is 117. Here sigma I equals 1 to m, that is pi hat, no. So then you can write p hat I equals 1.17, right? So we can use these answers for the further calculations. Then now here we have to revise the control limit. Then we have to find, we need to find the control limits, no, right? To find the control limits, first we have to, here p is not given, so we have to calculate the p bar. So p bar by using this equation we can calculate this equation. These two equations we can use. Then I am mentioning two methods in there. Here method 1, if you use this equation, p bar equals I equals m to di over mn, or you can use this equation also. Then here p hat equals di, sigma di we found this one, that is 117. So here 117, and m and n, m equals 20, here sample numbers there are 20, m equals 20, then n equals 100, so mn, then 117, 20 into 100, 2000. If we divide 117 by division by 2000, you can take 0.0585. This is the answer. And also if you like, you can use this method also. Then the other equation, sigma p hat I over n. So p hat I we found 1.17. 1.17 divided by m equals 20, then 1.17 divided by 20, again the same answer, you can take 0.0585. so now you found p bar. Now you found p bar. Now you can find the p chart. According to the standard is not given, so then this equations, this p is known, p is not known, this equation you have to use. Then p chart, p bar equals this is lower control limit. Upper control limit, you can find p bar plus 3 times p bar 1 minus p over n. So p bar you found as 0.085. so here 0.085 plus 3 times p bar, here again n equals 100. so after simplifying this, you can find the value as 0.1289, and center line equals p bar, that is this value 0.085. and also lower control limit, by substituting for this equation you can take the value as minus 0.0119. These are the trial control limits, but if you know that the d is number of non-conforming units, so d can't be 0. D is a positive integer, so if it goes to minus value, so we approximated that value for the 0. Note, if lower control limits took negative value, it should be approximated to 0. Then here if we take 0 minus value, so we take this as lower control limit as 0, not the negative values. Remember that. Right, then now we found the values. Then this is the upper control limit, and this 0 is the lower control limits. Now actually we have to draw the control chart by using these data, but I am not this data you have to draw the chart, but I am not going to draw the chart. But now I found that values. This is what is the value? 0.1289. right here, it means we can write 0.12. this one 0. no, now I am checking those values. Here the values not between, now the range is 0, then p hat I less than what is the other one, 0.12. 0.12. Where is it? Right, 0.12. the value should be here. We check those values, that is this one. Yeah, this one is in the range, correct. Yeah, that is also 0.01 is also in this range, right, correct. This one in the range, this one in the range. 0.06 also, 0.15, that is go beyond this, no, so that is not in the range. 0 is also not in the range, because that is not included 0, there no equal mark in there. This is in the range, and here 1289, no, so that we can approximate this for the 3. Why 128 means that is 13. so here we have to change as 13, then 13, then 0.01 range. Yes, all the others values are in the range, but we found this value, 13th one, this one, and the 12th one, this one not within the control limits. So then what is the theory? This is the theory. If the quality characteristics plotted the trial limits, if any point go out to the symbol cursor, should be removed. So these two need to be removed. Then here totally there are 20 in the sample. If this 2 is removed, so it becomes 18. So we have to revise the control limits now. We have to recalculate. So now here the observation in the sample 12, number 12 and 13 are not in the specified control limits. This one, these two are not in the specified control limits. Then what you have to do, you have to remove these two. It means, what are those two? What are those two observations? 15 and 0. You have to remove from this total also, right? So then we have to calculate again sigma di. Now sigma di is came as 117. No? So then if these two, if we removed, so we can find the new sigma di. Now m equals 18. Why? Because we removed 2. Earlier we had m as 20, but we removed 2 entries. Then m equals now 18. And here, if earlier we found sigma di equals, then this one is 15, the value of 12th one, the value was 13th one 0. So we have to remove this one, then we can find the total, that 15 plus 0, then mn again. Then if we remove this one, we can find the new p bar, that is 0.0587. No anything special thing, we remove these two. We remove these two and calculate. Then comes if we calculate this total, now you can find 102. That is the thing doing there. Now new value is 102, and now the new m value is equals 18. N is not changed, that is number of in the sample now, right? So then you can find p as 0.0567. 0.0567. Now again you have to calculate the control limits for the p chart. Now we have to use the new p value, that is 0.0567. Then here also it should be changed, that is wrong. Here 0.0567, and here also 0.0567. Then if we calculated these values, I think that should be correct. So we need a scientific calculator. We'll check because this is wrong. 0.0567 plus 3 times 0.0 another one, 0.0567 multiplied by square root is also taken, right? So it is difficult to do the calculation by using the computer, so use the calculator and check, then you can find the value. Upper control limit, here also again I wrote as low, this is lower control limit. Upper control limit as 0.1260, then p bar 0.0567 control limit, and lower control limit as again the minus value. It means you have to approximate for the 0. Then these are the revised control chart, control limits. That is the thing actually then asked from these types of problems, only things. Then if you if you learn these things, you can easily solve these kind of problems. And the next thing is the NP control charts. Now then earlier we considered about the P charts, it means non-conforming. Then NP charts, we are using the number non-conforming. Here it is possible, it is also possible to base a control chart on the number non-conforming rather than the fraction non-conforming. Earlier fraction non-conforming or the non-conforming, now number non-conforming, right? So if it is question ask number non-conforming, then you have to use the NP chart. This is often called the number non-conforming NP chart, control chart. So these are the control limits. If it is NP chart, so use upper control limit equals NP times plus 3 times square root NP 1 minus P, then center line equals NP, and lower control limit is equals NP minus 3 square root NP times 1 minus P. Here also the same thing. If the standard value for the P is unavailable, so you have to use the P bar to estimate P, as we discussed in the previous question. So here P is not given, so you have to calculate the P bar using the previous equations. All the equations we discussed in the previous example. So same thing you can use in these types of questions also. Then this is the example. Based on these data, if a NP chart is to be established, what would be the recommend as the center line control limits? Assume n equals 250. So the sample numbers are given. Number non-conforming units. Here number non-conforming units. Earlier non-conforming units. Now number non-conforming units are given there. You have to find the control limits for the NP chart. This is the solution. The sample number, again fraction you can find. Now n equals 250, no? Now n equals 250. Same equation you have to use. This is P hat I. So P hat I equals di over n. Now n equals 200. Here I wrote, no? It means di over 250. So if we need to find this one, di means 12 over 250. This one 15 over 250. This one 10 over 250. We'll check these values. 12 over 250, that is 0.048. that is correct, no? This one 15 over 250, that is 0.06. This one 10 over 250, that is 0.04. Then you can find the this is again, what is this? Is di, no? This is di. Then this one is sigma. Now m equals 10. Now m equals 10 because 10 entries are there. Sigma I equals 1 to m equals 10 di, that is 150. This one, what is pi? Sigma I equals 1 to 10 p hat I, that is 0.420. Then now easily you can calculate using the equations method. This p1, p bar, again m equals 10 and n equals 250. We found that is 105, no? Then 105, then mn also here given. If you simplify this, you can take this value 0.042 as same as the, if you like you can use the other method also. If we add these all values, it comes 0.420. If you divide this by m equals now 10, if you divide by 10, it's come 0.042. both answers are same. You can use any method you like to find the p bar. After finding the p bar, you can write the NP chart according to the this equation. this equation you can use to write the values. Then NP chart, upper control limit is equals to MP bar plus 3 times square root NP bar 1 minus P, then N equals 250. If we find here N equals 250 and P bar we found as what 0.042. if those two values is only enough, then NP bar we can find 250 multiplied by 0.042, that is 10.5. this is the center line, that is center line, and all the others here given. Then 250, then 3 times N equals 250, P bar is equals to 0.042. likewise by substituting those values and simplifying these numbers, you can find upper control limit as 20.0148, then lower control center line is 10.5, as well as the lower control limit as 0.9852. so this is the thing you have to consider about the NP chart. And as we discussed in the previous chapter, in here also we have to think about the OC curve and the ARL, average run length. That is the same, there is no change, theory is same. So as we discussed in the previous chapter, you can use the same way to find the beta, that means type 2 error, and also the average run length. The operating characteristic or OC function of the fraction non-conforming control chart is graphical display of the probability of incorrectly accepting the hypothesis of the statistical control, that is type 2 error or the beta error, against the process fraction of non-conforming. So beta error in this chapter also you have to find the number of non-conforming units, that is we called as D, follows a binomial distribution, right? So normally I explained at the beginning, these things are following the binomial distribution. So if means here, if you are using the probabilities, you have to use the binomial distribution, or sometimes according to the theories we learned in the introduction to probability theory, we can approximate this binomial distribution to the Poisson distribution. If you approximated the Poisson distributions, you can use the Poisson Poisson values also. Otherwise you have to use the binomial values if you find in the probabilities, and if you are finding the beta error and the probability of P, let P be a standard value for the fraction non-conforming. The probability of conforming a type 2 error is, that's the equation, beta P hat less than UCL in the pth probability, subtraction B beta hat, or these two equations, any one of these two you can use to find the beta error. So this is the example. So then now we can through this example you can understand how you can find the type 2 error or beta error. Consider the fraction non-conforming process where the sample size is 50. Where the sample size is 50, it means n equals 50. Have been collected, and upper and lower control limits are upper control limit 0.3697 and lower control limit equals 0.0303 respectively. Important to detect a shift in the true fraction non-conforming is 0.3. then P is given, that is 0.30. In this case no need to find the P bar because P is given. What is the probability of committing type 2 error if the shift has occurred? So you need to find beta in there, right? For find the beta you have to use this equation. Here I think you have to use this equation because no need to find P hat. P is given. If P is known, so you have to write N UCL P, this value, these equations you need to find. Right, so this is the solution. So n equals 50, P equals 0.3. We wrote those things in this here, right? Okay, and so this is the equation. P d sub d n equals 50, so you can substitute 50 there. Then upper control limit 0.3697, yeah, that's correct. Then P equals 0.3. Subtraction d less than or equal 50 times lower control limit, that is 0.0303, right? 0.3. So you can multiply these two, then it's come as 18.845. Here if you multiply these two, it comes 1.515. However, d must be an integer. D is the number of non-conformant units. Units means it can't cannot be decimals. These are the attribute data. So these are the attributes means it can't take the decimal values. So 18.85, that's if it is greater than 18, normally we are taking the least value. It means here if 18 point something, you have to take that as 18. That 1 point something, you have to take that as 1 point. Here also if you take another value 20.14 something, then value is 20. We approximate for the whole number only, right? So then I am taking beta p d less than 18 in the 0.3 probability, and p d less than or equal 1, that's 1.5 approximated at 1 in the 0.3 probability. So you have to, I told you these things are from the binomial distribution, so you have to use the binomial table. This is the binomial table. So then here that n equals 50, here n equals 50 and x equals 80, these are the values, and the probability is given there, that is a probability. Here 0.3 probability, here this probability you have to use. This is the 0.3 probability, and 0.3 probability, n equals 18, that is come this value 0.8594, here 0.8594, and also you have to find 1 also in 0.3. then here that is 18, no, 1 is here 0.031, that is here 0, the value is 0. So you have to substitute those values. Then 0.8594 subtraction 0, then beta you can take as 0.8594. so that is the error, that is a type 2 error. So then finally that this in the part 1, in this video I am going to discuss only two types of charts, P charts and NP chart. And in that's another thing we discussed, we have to find the average run length. So ARL, average run length for the fraction non-conformant control charts can be found as before means the chapter 3 we found in, if it is in control, that's ARL naught we taken as 1 over alpha. If it is in out of control, ARL 1 we can take 1 over 1 minus beta. So now beta is found, so average run length we can find. Suppose the process of shift P equals 0.3, then beta is equals 0.8594, then ARL you can find 1 over 1 minus beta. After beta you found 0.859, then 7.17. So here also I told you these are the attributes, the non-conforming units. It means if it is 7.1 point something, that's you can approximate that as 7. Those are the things I am going to discuss in this video. So I now I completed control charts for the P chart and NP chart. So we have to discuss another two types of charts, that is C charts and U charts. We discuss those things in the next video. So there are 3 examples, so do individually in these examples. I didn't explain explain each and every steps. I explained only the methods, but you have to do individually and understand so how to do those calculations, because based on these calculations you have to submit the tutorial as well as the in the final examination you have to answer those questions. So uh, clearly understand what you have to do, how to do the simplification by using the control charts for the attributes. If you have any problems, feel free to contact me anytime and clarify your doubts before submitting the tutorials. So first do these 3 examples again by yourself, and then if you have any problem, please let me know. Right, thank you very much.